Hey everybody. Today's lesson is Hess's law equation. I don't know why I was going to say heat. Hess's law equation and stoichiometry with heat. So we in the past have been looking up the heat of formations, and we've been doing so using this table, this thermochemical data of selected elements and compounds at 25 degrees Celsius, so standard temperature and pressure. And we've been using this table to use and calculate those values. And so we're able to look up the heat of formation for any given compound. However, if we are not dealing with a heat of formation reaction producing 1 mole of a compound, we currently have no way of finding the heat of that reaction. Fortunately for us, Hess has provided us with an equation we can use that will help us calculate the heat of reaction for any reaction. And it's this simple formula. Um, there's a couple fundamental math rules that exist in life. And one of the rules is that it's always final. Whenever you're looking for the change in something, it's always final minus initial. And in this case, it is the delta H, the enthalpy of the products, minus the sum of the enthalpy of the reactants. Again, final, the products, minus the initial, the reactants. And that will give you the overall enthalpy, the delta H value. And so the E sign means the sum of, as we've talked about, H values for the products and the reactants. Remember that the delta HF values must be multiplied by the balancing coefficient. So previously we talked about, well, let's just make all of these equations equal 1 mole. So when you have something, it's just like 1 mole of it. However, if it has multiple moles, well, then we could just multiply the delta H value by whatever the balancing coefficient is. And that's what this point here says. You can only use the raw value on the thermochemical data sheet if the coefficient in front of the compound is 1. The other thing we need to pay close attention to is the state. And so here are some common mistakes that people make is they forget to multiply the delta HF values by balancing coefficients. And so what they do is they just look at this table and say C6H6 has a value of 49. Let's just take 49 and let's use that value. That is a common mistake people use when the balancing number might be 6. So you need to take 49 times 6. Using the wrong value, so H2O gas instead of liquid, yes, they are different values. This is a common mistake going reactants minus products instead of products minus reactants, or putting the wrong sign on values. Those are all common errors that people end up making that we need to be really careful and keep track of. So, using Hess's law equation, calculate the heat of the reaction for the combustion of benzene C6H6 as shown by the following reaction. So we have C6H6 liquid plus 15 over 2 oxygen gas times 6 carbon dioxide gas plus 3 H2O. So what we want to do is we want to go and find the delta HF. And to do so, we're going to take the products here and we're going to subtract the reactants. And so I'm going to put in brackets here this first value. I know that whatever value for carbon dioxide gas I get, I need to multiply that by 6. So I'm already going to write the 6. And then we would look for carbon dioxide gas, CO2 gas has a value of negative 393.5. So I'm going to go 6 times negative 393.5. Oops. Negative 393.5. Let's erase this little nub. And then we want to add that to, remember, this is all the products. We want to add that to whatever H2O in the liquid state is. So 3 times bracket. H2O in the liquid state is negative 285.8, negative 285.8 bracket. And then we can close that entire bracket off. So that's all of our products. And then we want to subtract the reactants. And so the reactants, we have C6H6, which exists right here and has a delta H value of 49 and has a balancing number of 1, so I don't have to multiply it by anything. And we want to add that to 15 over 2. So whatever we have is going to be for O2 gas, we're going to times it by 15 over 2. And then O2 gas exists right here. It has a delta H value of 0. Delta H value of 0. So then what we want to do is we want to combine all of these numbers together. So we have 6 times negative 393.5 plus 3 times negative 285.8. And we will get a final value here of negative 3,218.4. And we want to subtract, in this case, this just remains 49. So we have that negative 3218.4, subtract 49 from that, and we will end up getting 3267.4 kilojoules. And so kind of the key ideas here is that this was the sum of the products, which is why we included the plus sign. And then we wanted to subtract the reactants, the sum of the reactants, which again is why we had this plus sign here. So that's our first example there. Stoichiometry, inviting heat, just some common last little pointers that we need to discuss. If something's exothermic, it has a negative delta H, energy is released, energy appears as a product, and the surrounding increase in temperature. If it's endothermic, energy is absorbed, and that energy appears as a reactant, surroundings decrease in temperature. So we have a calculation question here, which is how much heat is transferred when 9.22 grams of glucose, C6H12O6 in your body reacts with O2 according to the following equation, where we have C6H12O6 plus 6O2 goes to form 6CO2 gas and then 6H2O with liquid. And fortunately for us, we have been given the delta H value. We've been given a delta H value of negative 2,803. So that was really nice of them to do for us. So what we would do is basic stoichiometry here. We start with this 9.22 grams, and we try to convert. Into the moles here of C6H12O6. And then when we do so, we know that for every 1 mole of this, our balancing number is 1. We also are releasing 2,803 kilojoules. Now, they didn't include the negative sign, but you could if you really wanted to. Either or, it doesn't matter. This 180 grams, this is the molar mass of C6H12O6, which is glucose. And then you find out that you release 143 kilojoules. So that's really quickly just the PowerPoint that we were going to go through. Just kind of going over Hess's heat law. Hopefully that was helpful. If you have questions, please let me know. And then we can go from there. We'll do one more example here really quickly. Again, same type of question. How much heat is transferred when 147 grams of NO2 is dissolved in an excess of H2O? Again, this is nice because we know we have an excess of H2O, meaning we know what the limiting reagent is. This is the limiting reagent. And because it's the limiting reagent, we can start our question with the 147 grams. Again, we have the molar mass here. And then we can convert into kilojoules. Now, this 3 moles here, this is from the balancing number out front here. And so for every 3 moles of NO2, we're releasing 138 kilojoules. And then we end up getting the exact same answer that we had last time. So that is really, really quick PowerPoint on Hess's heat law. Hopefully you enjoyed and learned something along